Well, welcome back, and we're going to basically look at the second part of electrolysis reactions. The first electrolysis reactions that we looked at are all non-spontaneous reactions, but we only really talked about the electrolysis of a molten salt, where we don't have any water present and we've melted the salt down. Now we're going to look at some conditions that are a little bit non-standard. So one of the things that you need to think about is in an electrolytic cell, remembering there's no separation, and we have our battery connected to our positive and our negative electrodes. Okay, if we were to electrolyze water, okay, just straight water, we could produce hydrogen gas and oxygen gas. Okay, but if now we add in some sodium chloride into our solution, we now have multiple things. The water could undergo electrolysis, the sodium can undergo electrolysis, and the chloride ion could undergo electrolysis. So we could be producing hydrogen gas, we could be producing oxygen gas, we could be producing sodium or chlorine. And we don't know which one's going to react. Okay, so in the case of our competing reactions at the anode and the cathode having different oxidizing agents and different reducing agents, we actually need to be able to predict which one would react. Okay, so the rule is that the strongest oxidant will always react at the cathode and the strongest reductant will always react at the anode. So if that's the case, we need to look at our electrochemical series. Okay, if you remember, we have our strongest oxidant on the bottom left-hand side and our strongest reductant on the top right-hand side. Okay, and usually we're looking for a positive gradient. Okay, that's not going to happen with an electrolytic cell. What we're doing is we're forcing the reverse reactions to occur. Okay, but the strongest oxidant is still going to be oxidized and the strongest reductant is still going to be reduced, which means that if we've got all of our chemicals listed, our ions and our reduced species, okay, then we're going to circle everything that's present and only everything that's present. Okay, so our strongest oxidant is reduced. Now that means that Na plus, okay, is capable, that is present in our cell, and if we have a look, we would have a water down here that would be capable of reacting in our cell. And then in the case of chlorine, okay, we would have our chlorides and we would have our waters as well. Okay, so if this is my strongest oxidant, if I run my finger up from the strongest oxidant and wait until I hit one that I've circled, so we only circle the ones that are present in our cell, that's going to be my strongest oxidant. Okay, so it's going to be reduced, so the reaction will go this way. Okay, and then I'm going to run my finger down from the top for my reductant, okay, and this is, in this case I'll hit water, and that one will be oxidized. So if you look at this situation, if the strongest oxidant and the strongest reductant always react, okay, then we're not going to actually ever see sodium and chloride reacting in our cell. Okay, so what we will see is will be hydrogen gas and oxygen gas being produced. So this is what that looks like. When we're looking at the electrolysis of an aqueous solution, it becomes challenging to predict. Okay, so we have the ions of the ionic compound, but we've also got water. This rule always applies. The strongest oxidant will always react with the strongest reductant, and reduction always occurs at the cathode. Okay, so we check the electrochemical series. Okay, we have inert electrodes. The reason we have inert electrodes, because if you think about this, if the electrodes weren't inert, then that metal solid has the potential to be oxidized. So it adds yet another competitor at our electrodes, and that can make the situation quite complex, and you need to look out for that. But in this case, we will electrolyze water. So we'll produce oxygen gas and we'll produce hydrogen gas. So we'll produce hydrogen gas at the cathode and oxygen gas at the anode. Okay, as we apply a current. And so we will never actually see sodium metal, which makes sense because if sodium is going to be around water, it's going to be reacting. Okay, it will have a spontaneous reaction with water. So we're not going to see sodium metal being produced, and we won't see chlorine gas being produced. We'll just see water. And this is the case for most of our highly reactive metals. So things like potassium and sodium and even magnesium. If they are in a aqueous solution, we won't see them being produced. Okay. The other thing that we need to look at is the concentration conditions, because remember that the electrochemical series is at 25 degrees C and 1 molar concentrations for solutions. The E0 value, so the electronegative potential, okay, for the cell of chlorine is 1.36 and for oxygen is 1.23. They're very close. And what happens then is if we boost up the concentration of the solution, making it a non-standard conditions, therefore making what we call a brine solution, which is a very concentrated, saturated solution of sodium chloride, instead of seeing hydrogen gas and oxygen gas like we did in the previous dilute aqueous solution, the ions, we have a lot of chloride ions present at our anode now. So these chloride ions, because they're there with an excess of electrons or dearth of electrons, and there's lots of them around at a high concentration, what we end up seeing now is chlorine gas being produced at at those voltages. Okay, so the electrolysis of brine is important to the chemical industry because now we can produce chlorine, okay, as well as hydrogen gas, which are both useful. Okay, and you'll notice that we're also producing, we're getting hydroxide ions in here when we produce the H plus into hydrogen gas. We're actually getting lots of useful chemicals out of this. But the key thing to remember is that when it is a concentrated solution of an ionic salt, we need to check because those halogens can start to form their gases. Okay, so they can be oxidized at our anode instead of water, and that's with concentration considerations. Okay, and then we can use this chlorine for a large number of industrial purposes. Okay, so summing all this up, we need to know the difference between a voltaic cell and an electrolytic cell. So for a voltaic cell, oxidation occurs at the anode, which is negative. For an electrolytic cell, oxidation still occurs at the anode, but this time the electrode is positive. Reduction will always occur at the cathode in both cells, but the polarity of that electrode changes. For a voltaic cell, the cathode cation positive. For an electrolytic cell, the cathode is negative. Okay. In a voltaic cell, we are producing voltage. We are producing electricity from a spontaneous reaction. Whereas in an electrolytic cell, we are using energy to force a non-spontaneous reaction, the endothermic process, to occur. Okay, so we have chemical potential energy being converted into electrical energy, and then we have electrical energy being converted into chemical energy in the electrolytic cell. Okay, discharge is when the cell is producing electricity. Okay, and therefore we have cathode being positive, anode being negative. Okay, during electrolysis, the battery is determining the polarity of the electrode. For a voltaic cell, we must have two separate half cells that are connected by a salt bridge to complete the circuit along with an external circuit, and they will generate electricity. Whereas with electrolysis, it's a molten liquid, so we want the molten salt, or we can have aqueous solutions, but then we need to consider competition at the electrodes. So that's our summary of electrolysis. Now it's all about looking at as many cells as we can and examples as we can to become comfortable with the process.